Welcome back, folks. We are doing a little bit of backtracking here as we move forward. No pun intended. Backtracking, moving forward. You get the idea. We're going to be focusing today on some more of the mathematical aspects of chemistry and really hunker down into the process of building and putting together chemical reactions. What we're also going to do is we're going to type these chemical reactions, that is, identify how atoms are exchanged in these chemical reactions based on their reactants and products. We're also going to spend a little bit of time doing some mathematical calculations and converting between atoms, molecules, grams, and a term known as moles. So lots to cover today. But hopefully by the end of this, you'll have every idea cemented into your head about how we do these chemical calculations, determination of chemical formulas and chemical reactions, and how we predict the products of certain types of chemical reactions. So our goals for this video are pretty straightforward. My goal for you guys is to understand the conventions when writing chemical equations. You should be able to balance an equation given the chemical formula for all reactants and products, know the defining characteristics of chemical reactions. You should also be able to recognize the following chemical reaction types. That includes combination, decomposition, displacement, and combustion. We should also be able to calculate the formula or molar mass of a substance, given its chemical formula and atomic mass. Be able to know the value for the counting unit, which is called a mole. Calculate the number of particles, given the moles of a substance, and mass in grams. Interpret subscripts of a chemical formula, given the number of moles of various elements given in the molar mass of a substance, and convert between atoms, moles, and grams of any substance. So we really are focusing in on just some of the mathematical aspects, mathematical routines, if you will, in regards to chemistry class. In addition to that, we will also be focusing on chemical reactions, how we write those chemical reactions, how we predict the products of those chemical reactions, how we go through and balance them, really anything chemical reaction related. That's our primary focus for this unit. So we're going to start off by diving into chemical reactions and understanding the process of how we write chemical equations and how that represents a chemical reaction that's taking place. A chemical equation is a written statement that uses chemical symbols and chemical formulas to describe a chemical reaction that is taking place. And so you have an example here on the right of the combustion of CH4, which is known as methane, reacting with oxygen gas to produce carbon dioxide and water. Well, rather than having to go through and explain that orally or utilizing words to be able to describe that, we can write out the formulas and write a chemical reaction utilizing a couple of conventions. We use the term reactant to describe the starting material in a chemical reaction, that is the material that is on the left side of the arrow, and we use product to describe the products or the ending material of a chemical reaction, which is on the right-hand side. The arrow is representative of the term yields or produces, so everything on the left is your reactants, that is what we have prior to our reaction, and what we have on the right-hand side of the arrow is our products, or what we have at the end of a chemical reaction. In addition to that, you may see states of matter that are described next to the chemical formulas that are listed. G is representative of gas, S is representative of solid, L is that of liquid, and AQ is representative of an aqueous solution, which is just simply an ionic substance that is typically dissolved in water. So for example here, I would use the terms calcium sulfide reacting with water to produce calcium oxide and hydrogen sulfide. So knowing your nomenclature is going to be very important here because we need to make sure that we write out our chemical formulas correctly. So in the example here, you see that CaS plus H2O yields CaO and H2S, and we'll talk about how we predict that a little bit later on. But in the very first line, you see what's highlighted is CaS and H2O, and what's highlighted here are our reactants. That is the materials that start the chemical reaction. What we have at the end in line number 2 that is highlighted is our products. That is what we have at the end of our chemical reaction. The arrow represents the yields sign. That is the difference between our reactants, which are on the left side, and our products, which are on the right side. And then the plus sign is just reacting with and something that's in addition to a reactant. So here we have 2 reactants and we have 2 products. The plus sign indicates that we're reacting those 2 chemicals together, or if it's on the product side, those are the 2 chemicals that we get out of our chemical reaction. So again, we have our reactants, our products, and then the arrow represents yields or produces, and the plus sign represents the term reacts with or and. In addition to making sure that we know all of the chemical formulas that are written on the periodic table, some elements cannot exist by themselves. These are known as diatoms. Di meaning 2 and atom meaning atom, and there will be 2 of each element. So if these are ever by themselves, they're paired up with themselves. So bromine by itself will not be Br, it will be Br2. Iodine will not be with itself, it will be I2, nitrogen, chlorine, hydrogen, oxygen, fluorine, etc. In some instances, I refer to them as Brinkelhoff. It's just an easy little acronym for me to be able to remember what they are. Or in addition, you can also use the 7+1 method in the fact that they represent a 7 on the periodic table, and then +1 is indicative of the hydrogen that is on the left side of the periodic table. These are all of your diatoms. These are your only diatoms that are found on the periodic table. And again, these are based off of when they're by themselves. Remember, if these elements are in chemical compounds, what indicates the number of atoms present in that compound has to do with the charges that are represented in the ionic substance. So when I say, again, be consistent with information that's given in the word equation, this means that all nomenclature rules learned previously still apply, especially when we have to go through and write out chemical reactions. In addition to making sure that we write out our chemicals correctly, one other thing we need to take note of is the balancing of chemical reactions. The law of conservation of mass applies to all chemical reactions. That is, the number of atoms that we have present at the beginning of our chemical reaction must be the same as what we get out of the chemical reaction at the very end. So by following the law of conservation of mass, we have to balance. And by balancing, what we do is we put coefficients in front of our chemical formulas that is written correctly. This is different than a subscript. If I take a look at the example on the right-hand side here, the subscript only affects the hydrogen that's there, indicating that there are 2 hydrogen for every 1 oxygen, hence H2O. But a coefficient in front applies to both the H and the O. It's a simple way of thinking of it is like the distributive property of math, right? The 2 applies to the H2, meaning that in that we have 4 H's, and we have 2 oxygens because the 2 applies to the single oxygen that's on the right-hand side. So once we've written all of our chemical formulas correctly, we balance. We put coefficients that are in front to ensure that the number of atoms that are on the reactant side of my equation are the same as the number that are on the product side of my equation. A big thing to keep in mind here is that when you're writing your equation, you cannot change the chemical formula. So when we go through and balance it, you can't change that. If you change the formula, you change the identity of the substance, which we simply cannot do. An easy way to do this is to simply alternate back and forth between balancing your reactant and product to balance your equation. Some people like to make a chart showing the number of atoms that are on each side to help keep track of this balancing process. And a lot of that just depends on how you process this information. If you're good with numbers, you should be able to work back and forth fairly easily in order to be able to balance a chemical equation. Sometimes it's best to write out a little chart in order to help you go through and balance these out. So as we take a look at the equation that we have here, we can see that it's already balanced. And again, that is based off of the coefficients that have been put in front of each chemical on the reactants and product side. So for my reactants, you'll notice that I have a 4 in front of NH3, a 3 in front of O2, a 2 in front of N2, and a 6 in front of H2O. Well, how does that impact the number of each individual atom that's on each side of my chemical equation? Well, if I take a look here, I have 4 nitrogens that are here, and 2 N2s on the opposite side, which again is indicative of a total of 4 nitrogens. If I look at hydrogens, there's 12 on each side. That 4 applies to that 3 for a total of 12 H's. 6 H2s, same thing. We have 12 hydrogens on the right side of the arrow. The last thing I want to look at is the number of oxygens. 3 O2s is indicative of 6 oxygens. And same thing here, that 6 applies to that oxygen, giving us 6 oxygens as well. So the big thing I want you to see here is how a balanced chemical equation looks, right? We have the same number of each atom on each side of the equation. Now the tricky part here is figuring out exactly what we need to do in order to make this happen. So if I take a look at the bottom question here, I've got FeI2, Cl2, FeCl3, and I2. And so if I go through and I look at these, the way I want to figure out where to start, and there's a couple of little strategies and tips I'm going to show you as I work through it, but is to look at what's different on each side of the equation. Irons are the same, iodines are the same, but chlorines are different. There's 2 chlorines on the left side of the equation, and 3 chlorines on the right side of the equation. Well, there's not a number that we can put in front of just one of these in order to get them to balance, but if we know a little bit about math, we know that the least common multiple of 2 and 3 is 6. So if we can get both of our chlorines to be 6, we'll know that they are balanced. So we'll put a 3 in front of Cl2 to give it 6 chlorines, and a 2 in front of FeCl3. So that makes a total of 6 chlorines on each side, and we've gone through and balanced the first part of our equation. Now, how I do this is I look at what has changed after I've gone through and balanced. So my chlorines are now balanced, but what changed here is I now have 2 irons on the right side of my equation, whereas I only have 1 iron on the left side. So in order to balance that out, I need to put a 2 in front of the FeI2. That results in a total of 4 iodines, So a 2 needs to go in front of I2. So do you see how I'm working back and forth? I start with one point of contention, and then I kind of work back and forth between my reactants and product side in order to figure out how to go through and balance my chemical equation, okay? So there's a couple of other tips and tricks that we're gonna show you, but that kind of covers the gist of how we go through and balance our equations. Now again, you can create a chart, and I see some students do this. They create what I like to call an RP chart, and they just take each element, so FeICl, and they basically start off with the number on each side of the equation, and they just kind of work back and forth to balance it. It's the same thing we do here. It's just in a little bit more regimented, formatted way, whereas this is a little bit different as it doesn't require as much extraneous work, especially if you're good with math. The way I showed you how to do it should be just fine. So that being said, let's move on. All right, so I wanted to provide you just a couple of my own personal hints. These are ways to just make this a little bit easier on you because there is no real one right way to go through and balance a chemical equation. It does require some trial and error. It requires some technique. And like I said, there's just no one right way to do it. It just takes practice and understanding what you're looking at. So a couple of hints. If you're struggling balancing, check to make sure you wrote your reactants and products correctly. So if they're given to you, you can probably make the assumption that they're already written correctly. But if I'm making you go through and write out the chemical formulas before you balance, and you're having a real hard time going through and balancing an equation, double check to make sure you wrote them correctly. In addition to that, if you're balancing polyatomic ions, try to keep them together when balancing. So for example, if you see SO4 on the left and right side of the equation, don't break it down into S and O and try to balance them separately. It becomes very, very confusing to do it that way. But rather, treat SO4 as just a single ion, kind of like what we do when we do nomenclature. If we treat it as its own independent thing, it makes it a lot easier to balance the chemicals on each side of the equation. Lastly, make sure that your coefficients are in the smallest whole number ratio on each side of the equation. So I have a balanced equation here in red that's 8, 4, and 8, but that is not in the lowest whole number ratio. 8, 4, and 8 have the ability to be reduced to 2, 1, and 2. So we want to try to reduce that as much as possible. It doesn't happen very often where if you're working kind of back and forth, you end up with numbers that can be reduced, but I did want to make sure that you are aware of that is something that I do see on occasion when we go through and balance equations. So I want you to try these on your own. I'm going to work through them just like we normally do, but take a minute, pause the video, and try to work through and balance these independently. And we'll be back in just a moment to go through them together. All right, so hopefully you're able to take a moment and go through and attempt to balance these chemical equations. One other rule I did want to talk about is that if you're given an option on where to start, try to pick the thing that is the most difficult to balance. So if I look at this very first problem that's here, iron 1 and 2 is pretty easy to balance, but oxygen 2 and 3 is going to require a least common multiple situation, just like what we've talked about previously. So oxygens need to be 6 here. So we need to put a 3 in front of O2 and a 2 in front of Fe2O3. That results in 4 irons. So a 4 goes in front of the Fe. So again, this is just a process where we methodically work back and forth to try to figure out how we're going to balance our equation here. For the next one here, I notice I have 3 oxygens to the right side of the arrow and 1 to the left. So let's put a 3 in front of FeO. That results in 3 irons. So we need a 3 in front of Fe. And then you have a 2 in front of aluminum here, so a 2 needs to go in front of the Al in the first part of the problem here. Once again, we run into a question that's going to be a little bit on the challenging side to go through and get here. I have 3 oxygens in Fe2O3. I have 1 on the right, so let's put a 3 here. That results in a total of 6 hydrogens, so a 3 goes in front of H2 to give it 6. And then a 2 in front of Fe. So again, it's just a methodical process of working back and forth in order to figure out exactly what you're trying to put together here. The last one contains a polyatomic ion, so I want to go through and balance that as a whole. So rather than breaking down nitrogen and oxygen separately, what we're going to do is we're going to just balance the nitrate ion as a whole thing. So there's 2 NO3s and 3 NO3s, so we need a total of 6 NO3 ions. So a 2 goes in front of here, a 3 here, and then we just finish it up by balancing our aluminum and our lead. So again, it is a step-by-step methodical process. Practice, 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 and I promise you'll get really good with this. All right, so again, I noticed that there's a lot here. The only difference between this and what we've done previously is I'm going to ask you to write out the formulas for those equations. So it's very important to figure out what we're looking at in regards to each equation, what chemicals we have in states of matter. Solid sodium bromide and aqueous calcium hydroxide react to form aqueous calcium bromide and aqueous sodium hydroxide. So Remember that react to is your arrow, the and is your plus sign. So if we break it down like this, it makes it very easy to figure out what goes where. So start off by writing your formula. So solid sodium bromide, so NaBr. Anytime you write out a chemical formula when you're trying to balance a chemical equation or write an equation, always make sure that you check the charges to make sure that you've written the chemical formula correctly. So sodium bromide as a solid reacts with aqueous calcium hydroxide. So remember that is a polyatomic ion, OH, 2 plus, 1 minus, so CaOH2. React to form aqueous calcium bromide. And aqueous sodium hydroxide. Again, notice I'm always checking my charges. Include states of matter if they're given. And then now what we do is once we finish writing out all of our formulas correctly, we just go back and balance it. I have 2 OHs to the left side of the arrow and 1 to the right, so a 2 goes in front of NaOH. And then you're going to put a 2 in front of NaBr, and that ends up balancing our sodiums and our bromines on each side. So again, notice it's just very methodical. It's very step by step. You take your time, you do one thing at a time. First thing you need to do is write out your formulas. Make sure you write them out correctly. Then write out your states of matter, and then go through and balance your chemical equation. Let's do one more. All right, so we're going to highlight it just like we did last time. Gaseous hydrogen bromide reacts with solid aluminum hydroxide to produce gaseous water and aqueous aluminum bromide. So we follow the same steps we did before. Hydrogen bromide, or hydrobromic acid, is HBr. And again, you can check your charges, 1 plus, 1 minus. Oops. Reacts with solid aluminum hydroxide, 3 plus, 1 minus, to produce water, gaseous water, and aluminum bromide. Again, check your charges every time you do this. All right. So what I would recommend here, and this is something that I typically do with water, especially if I have a polyatomic ion. So if you look at the example here, on the left-hand side I've got OH minus, but I don't have it on the right-hand side. What I'm going to do here is I'm going to change H2O into H and OH. And so that makes it a little bit easier to balance because I have my OHs here that I can go through and balance independently. So 3 OHs on the left side of the arrow, 1 on the right, a 3 goes in front. That gives me 3 H's by themselves. 3 goes there. 3 bromines and 1 aluminum. So we're set here, other than the fact that I forgot to include aqueous down here. So again, it just take it one step at a time. It's just practice, practice, practice. That's all this ends up being. All right, now I want you to do it on your own. Try this out, see how it goes, and we'll come back and look at it in just a moment. All right, solid copper oxide breaks down into solid copper metal and oxygen gas. Again, we put our little arrow here and our plus sign, so let's write this out. So copper 2 oxide, so that is CuO, 2 plus, 2 minus. That is a solid. Breaks down into solid copper metal. Okay, so anything by itself. Just Cu, and oxygen gas, that is our diatom. So again, double check, make sure you've written everything correctly. Now go back and balance. 2 oxygens on the right side, 1 on the left, a 2 goes in front, and then a 2 goes in front of copper. So again, it's just a work in progress to just work through and balance those equations. Let's try one more here. We have aqueous silver nitrate reacts with solid iron metal to form aqueous iron nitrate and silver metal. And again, we break down what reacts with is our plus sign to form as our arrow and as our plus sign. So same steps as we've done before. So silver nitrate, Ag, NO3. Again, check your charges. Reacts with solid iron metal. Anything by itself has no charge. We form iron 2 nitrate, so FeNO3. 2 plus, 1 minus, so FeNO3, 2. And silver metal, which is Ag. All right. Now we go back and balance. As I recommended to you before, polyatomic ion balancing is probably the best way to start this. We have 2 nitrates on the right side, 1 on the left, so put a 2 in front. And then 2 AGs, it's going to result in 2 in front of silver over here. So again, a back and forth in order to figure that out. Hopefully you did well with that. We're going to continue on with different types of chemical reactions. We'll learn how to predict those products and do a little bit more math. So stay tuned. We'll be with you in just a moment. All right, so our next step in working with chemical equations, other than just writing them out and balancing them, is to determine what type of reactions there are. And chemical reactions can be very easily classified based on how the atoms are rearranged on the product side from the reactant side. And there are 5 different ways that we typically classify chemical reactions. We classify them as either combination, decomposition, displacement, exchange, or combustion. And the way we go through and identify these different types of reactions is based off of the nature of the reactants and the nature of the products that are produced from the reaction. In some instances, we'll start off with 2 reactants, they become 1, or 1 reactant becomes 2, or there's a displacement of an atom or an exchange of atoms. We'll go through each one of these individually and discuss how we can identify them, and then eventually how we can actually predict the products of those chemical reactions. So the first type of chemical reaction I want to discuss is what is known as a combination reaction. This is a chemical reaction in which a single product is formed from 2 or more separate independent reactants. And so we have a myriad of examples that are here. These can be elements or compounds, but again, the easiest way to determine whether I have a combination reaction or not, and sometimes this is referred to as synthesis, just an FYI, is that I start off with 2 reactants and I get 1 product at the end. So at the very beginning there, I have hydrogen and nitrogen, it becomes ammonia. We start with 2 reactants, it becomes 1 product. Magnesium oxide and carbon dioxide are both compounds, but they still form 1 product, so as a result it is a synthesis or combination reaction. Same with CO and oxygen, and Na and Cl, they're all combination reactions because 2 reactants form a single product on the right side of the equation. The opposite of that is what is known as a decomposition reaction. This is a chemical reaction in which a single reactant is converted to 2 or more products. So essentially it's the reverse of a combination. We start with 1 reactant and we end up with 2 products as a result of that chemical reaction. So they can be elements or compounds. Looking at the first example there, we have iron hydroxide, and that decomposes into iron oxide and water. Water itself decomposes into hydrogen and oxygen. Silver bromide can decompose into silver and bromine, carbonic acid into carbon dioxide and water. Again, the nature of this is that 1 reactant ends up becoming 2 products on the product side of your equation. A displacement reaction. This is a chemical reaction in which an atom or group of atoms displaces an atom or group of atoms from a compound. So notice here that this specific reaction starts off with an element plus a compound, and we get that on our product side. But what ends up happening is that the individual element that is on the left side ends up replacing one of the elements in the second compound in the chemical formula. So for example, in the very first one there, potassium reacts with water. Well, potassium is replacing one of the hydrogens in water to create potassium hydroxide and oxygen gas. Second one there, magnesium. The magnesium replaces the copper. The third one, the zinc replaces the hydrogen. And then the last one, the chlorine replaces the iodine. So you can see here there's a variety of different ways that we can have exchange of chemicals. But the big thing to keep in mind here is that it is more than likely going to be just an element plus a compound, and we get an element and compound as a product. One of the elements has essentially switched places with what you find in the compound. Now, how do we know what gets replaced? Well, a fairly easy way to remember this is that metals will displace metals, that is, they'll trade places, or nonmetals will displace nonmetals. Another way to look at it is that things that are positively charged will displace things that are positively charged, and things that would normally take a negative charge will displace things that are negatively charged. Look at the example of magnesium and copper. They trade places in that second equation, and that is because magnesium is a metal and copper is a metal. They both have positive charges. They're not going to bind together, but rather they're going to switch places. Same with zinc and hydrogen here. Even though hydrogen is a nonmetal, it has a positive charge. Zinc in its ion form typically forms a positive charge, so they will switch places, resulting in zinc chloride and hydrogen. Chlorine, however, is a nonmetal, and so notice that when it reacts with calcium iodide, it is going to switch out with the iodine rather than the calcium because the iodine also would carry a negative charge, similar to what chlorine would if it were bonded into a compound. So figuring out what displaces what is based off of the nature of the individual element that is by itself. If it's a metal, it will replace the metal. If it's positively charged, it will replace what's positively charged. And if it's negatively charged, it will replace what is negatively charged. The second to last type of chemical reaction we're going to look at is what is known as an exchange reaction. And this is a chemical reaction in which two substances exchange parts with one another to form two different substances. So essentially, these are going to be two compounds that exchange their negatively charged substances. The examples given on the right show just that. KBr and AgNO3 end up becoming KNO3 and AgBr. Again, those negatively charged ions are switching places. Notice that the polyatomic ions are not broken apart, they just switch spots. Na2SO4 and SrCl2 become NaCl and SrCO4. Again, we're trading places here when we look at our chemical reactions. So simply take what's negative, trade its places, and you know that you have an exchange reaction. The last type of reaction is very specific in the fact that a combustion reaction is a chemical reaction in which oxygen reacts with a hydrocarbon to form carbon dioxide and water. So even though the equations on the right aren't exactly what we're looking for here, the ones on the left are. You have some hydrocarbon, that is some compound that is formed from carbon and hydrogen. It reacts with oxygen and produces CO2 and H2O. So notice that the examples given on the left are very, very specific in terms of the chemical formulas and what types of products are produced. So it's very easy to recognize, provided you understand that a combustion reaction requires a hydrocarbon, requires oxygen, and produces carbon dioxide and water. So again, here we have our variety of different types of chemical reactions that we're looking at and the generalized formula for these. So I would make sure that you not only know these based off of what products are produced, but also get into the habit of understanding just the reactant side as well. Because eventually I'm just going to give you the reactant side, and it's going to be your job, based on the rules that we just discussed, to predict the products of those chemical reactions that are given. So now what I'd like you to do is take a moment, classify and balance the following reactions. We've got 4 of them here. Take a moment, go through them, and we will look at these here in just a moment. All right, so before we go through and balance these equations, we're just going to go through and determine their types, just like what we talked about. So we have 5 types we're going to discuss here. If I take a look at this very first one, we have a compound and a compound produces 2 compounds. It's apparent that whatever's negatively charged switch places as we look at the product side. So this is known as exchange. Here you have 2 things becoming 1, so that is going to be a combination. You have a carbon and hydrogen that reacts with oxygen to produce carbon dioxide and water, so this is combustion. An element plus a compound producing an element in a compound, this is displacement. All right, so now let's go through and balance these just like what we did before. So we've got 2 OHs on the left, I'm going to actually use a different color for this. 2 OHs on the left, 1 on the right, so 2 goes in front here. 2 sodiums now, 2 goes in front, and we're balanced. SO4 here is good. NH3, we're going to need a 2 here. And that balances everything out because we end up with 2 nitrogens, like what we have here. We need a total of 8 hydrogens. There's 6 here and 2 here. So that gives us a total of 8. For combustion reactions, balancing, CHO is what you need to know. Carbon, hydrogen, then oxygen last. So start with carbon, 5 on the left, 1 on the right, 5 goes in front. 12 hydrogens, 6 goes in front. Now, make sure you add up the oxygens from both products of your chemical reaction. So you have a total of 10 here, and 6 is 16. So this needs to be an 8. So make sure you work through those very, very carefully. Here we got PB, we got H3PO4. I'm going to go through and do the hydrogens first. So we'll do a 2 here and a 3 here. Again, least common multiple of 2 and 3 is 6. That gives me 2 PO4s, which I'm good with here. We need 3 leads, so a 3 goes in front, and we're done. So again, make sure you can work to figure out what types of reactions you're looking at, and then work back and forth in order to figure out how to go through and appropriately balance them. We'll be back in just a minute. So lastly, and arguably the most important thing that we're going to do with chemical reactions is to be able to predict the products of a chemical reaction. And it really does require a variety of things that we've already learned and combining them together in order to really be able to go through and write out these balanced equations. So let's walk you through it step by step on what we're going to do here. The first thing we need to look at is, based on the reactants, determine the reaction type. So remember, we've talked about the 5 different reaction types already. We talked about combination, decomposition, displacement, exchange, and combustion. We can determine what type of reaction we have solely based on the reactants themselves. So that's our very first step. Secondly, we want to be able to write out our simplest product form based on the reaction type. So if you remember, there were quite a variety of little miniature equations at the very beginning of each of the slides that showed the different types of reactions, like A plus B yields AB, or XY breaks apart into X plus Y. It's very, very important that you follow those steps and break them apart accordingly, but also we do not carry over subscripts unless we have polyatomic ions. Remember that subscripts are determined by whether something's a diatom or not, or by what other chemicals it's bonded to. Step 3 is to correctly write out the chemical in each of your products, so go through and balance out your charges, recognize your diatoms, all of that good stuff. And then lastly, balance your chemical equation. So if I look at the examples on the right-hand side, let's try to predict what types of reactions these are. We won't predict the products of these, but let's figure out what types we have going on here. The very first one is that we have two elements that are combining together, Mg and N2. So because they're two elements, they'll combine into one thing, so that is a combination reaction. The second one is an element and a compound. And again, if I go back and look at the other types of reactions we've looked at previously, we're going to know that that is a displacement reaction. The third and the fourth are similar in the fact that they're two compounds that are reacting together, so both of those are going to be considered exchange reactions. So again, we can determine the type of equation, what the type of reaction we're looking at solely based on the reactants themselves. If you need some help with that, go back, take a look, and see what formulas or what the basic formulas are for each of the 5 types of chemical reactions we're going to be looking at. So let's do a couple of examples of some practice problems here before we start moving forward and before I give you an opportunity to work on some of these on your own. So this very first problem here says that sodium reacts with gaseous oxygen. Let's take a minute and recognize what we do have. The first step is to determine the reaction type. And I notice that I only have 2 elements. I have sodium and oxygen. They're going to combine together in what is known as a combination reaction. So if I only have 2 elements to start off with, the only thing that they can do is combine into one thing. So therefore, I have a combination reaction. Second step is to write out the simplest product form based on the reaction type. No subscript carryover except for polyatomic ions. So if I start off with the materials, I have solid sodium, which is Na, and oxygen, which is a diatom, which is O2. And I react them to form my product. Now notice, no subscripts are carrying over. I'm just simply combining the 2 elements into one, and we'll focus on the rest of the part later. But again, don't carry over subscripts unless they are polyatomic ions. Step 3 is correctly write out each chemical in your products using your charges. So Na is a 1+ charge, O is a 2-, so we cross and drop. So our product is Na2O. And then lastly, we go through and we balance our chemical equation. So we have, looks like 2 oxygens on the left, 1 on the right. So a 2 goes in front of Na2O, and then we end up with 4 in front of Na. So again, it is a step-by-step methodical process that we work through in order to figure out how to go through and write out these balanced chemical equations. Now, that being said, I have some that I want you to try on your own, okay? Try these on your own. We have quite a few that we're going to work through. We'll do 1 page at a time, and then we'll come back and see how we do with this. So take a minute, and we'll be right back in just a moment. All right, so just like what we've done before, the first thing we need to do with each of these is determine what type of reaction it is. Potassium and bromine are reacting together. These are 2 elements. The only thing these 2 things can do is combine together into one thing. So this is going to be our combination reaction. Okay. Remember, when we combine 2 things, we're just going to do the simplest form of the product. So K and Br together, or metal before non-metal, just like we do with any of our compounds here. Now we just need to make sure we've written our products correctly. So check your charges, 1+, 1-, so we're good there. And the last step is to go back and balance it. So 2 Brs on the left side, 1 on the right, 2 goes in front of 2 KBr, and a 2 goes in front of K. So again, identifying the type is the very first step. Predict the products based off of the type, but do not carry over subscripts unless it is a polyatomic ion. Check your charges, then go back and balance. Hydrogen gas reacts with chlorine gas to produce 1 product. 2 reactants, 1 product. This is also a combination reaction. Hydrogen gas, remember, it is a diatom. Chlorine gas, also a diatom. 1 product. Check your charges, so 1+, 1-, so we're good there. Now we go back and balance. Okay? I know they're pretty easy at first, but again, identify the type, form the most basic form of your products with no subscripts, Determine the subscripts based on the charges. Go from there. The third one here, we start with one reactant. The only thing we can do with one reactant is break it apart. So this is going to be a decomposition reaction. So start off with HI. Break it apart. Now go back and check your charges. But remember, we're checking for diatoms as well. Hydrogen and iodine, both part of Brinkelhoff. Go back and balance. Silver oxide is decomposed. It tells you right there what type of reaction it already is a decomposition. Silver oxide, Ag2O. Break it down. Any element by itself has no charge. Oxygen is one of our 7 diatoms. And now we need to go back and balance. 2 goes in front of Ag, and a 4 goes in front of the Ag here. All right? So again, step by step, we take our time, we work through it methodically, we figure them out, and we work through them, all right? Let's do a couple more. Predict the products of these chemical reactions here. So solid zinc reacts with aqueous sodium sulfate. So let's go ahead and write these out first, and that will help us figure out what types of products we're dealing with here. Okay. So notice that we have an element and then we're adding to it a compound. So this is an exchange. Sorry. This is displacement. Now to write the most basic form of our products, remember we have to figure out what this zinc is going to replace. Metals replace metals. Zinc is going to replace the Na here. So when I write my most basic form of my product, it is going to be Zn, SO4, and Na. They traded spots. They don't combine together, but they trade spots in this balanced chemical equation. We check our charges to make sure we've written everything correctly, which we have, 2 plus 2 minus, so we're good there. Na is not a diatom, so we're good there as well. And now we just go back and we finally balance our chemical equation. And we're done. All right? This next one here, solid iodine. So let's write this out. Again, writing out our reactants really helps us figure out what our products are going to be. Tin, 2 chloride, so that gives tin a 2 plus charge. Chlorine's a 1 minus, so 2 plus, 1 minus. So once again, we have an element and a compound. So this is another displacement reaction. This time we're dealing with iodine though. Iodine, if you remember, is a nonmetal, so it's going to trade places with chlorine because chlorine is a nonmetal. So chlorine is now by itself. And the tin and the iodine go together. Chlorine's a diatom, 2 plus, 1 minus, and we're already balanced. Okay, so again, recognize what type it is, exchange, and then go through it and write out your formulas correctly. Let's do one more. We have lead 2 nitrate reacts with potassium iodide. So again, write out your formulas. Lead 2 nitrate. Remember, always check your charges when you do this. Potassium iodide. Check your charges to make sure you're writing all your formulas correctly. My aqueous isn't that great written, but you get the idea here. So we have 2 compounds that are here. 2 compounds, you're just going to switch out whatever's negatively charged. So Pb is now bonded to iodine, and potassium is now bonded with nitrate. We check our charges. Okay. And then we go back and we balance. We have 2 nitrates on the left, 1 on the right, 2 goes in front. 2 potassiums, 2 goes in front, and the iodines are now balanced as well. So once again, determine the type, predict the products based off of the type of reaction, no subscripts unless it's a polyatomic ion, add subscripts based off of your charges, and then go back and balance your equation. It is a culmination of all of the different things that we have combined together. But if you know what we're doing, we should have no problem with this whatsoever. All right, let's move on. All right, so I've gone through and shown you a lot with chemical reactions. The very last thing we're going to do with this particular unit is work between different quantities of a substance. So one of the reasons that we include this in this part of the unit is because part of balancing and creating chemical reactions is to figure out roughly how much product I'm going to get from a reaction. So let's say I wanted to make 25 grams of a substance, I don't know, some type of medicine. Well, I need to think about what types of chemicals I need to start off with in order to get 25 grams of each substance. How much of chemical A and how much of chemical B do I need to react together in order to get the 25 grams of product? So we use a fancy chemistry math and a balanced chemical equation in order to figure that out. If we really break down this beautiful diamond that's over here, let's say you end up with a half-carat diamond for one reason or another. It has 5.0 times 10 to the 21st carbon atoms. Well, how do I figure out how much starting materials I need to synthetically grow a lab diamond that is half a carat? I need that many carbon atoms. So I need to find some way to harvest those carbon atoms or utilize that many carbon atoms in a chemical equation in order to produce my lab diamond that's shown over here. So one of the ways that we do this is by what is known as formula mass, or sometimes this will be referred to as molar mass. Now, we've already done this before when we've looked at average atomic mass or atomic weight. It is the masses, or the sum of all the atomic masses of all atoms that are in the compound, and we use the masses that are found on the periodic table. So for example, NaF, we take the molar mass of Na, which is 22.99, and the molar mass of fluorine, which is 19, and add them together to get our AMU value. It's just in this instance, it's how many grams are in a mole of something. We'll talk about a mole here in just a minute. But notice that when I have more than one element in my compound, I need to take that into consideration when I go through and calculate the molar mass. So H2O, 2 hydrogens and 1 oxygen. So notice we multiply the molar mass of hydrogen by 2. When we're dealing with something like NH4, 2, CrO4, that 2, remember it's distributive property of math, that 2 distributes to the nitrogen. 2 H4s is 8 hydrogens, 1 chromium and 4 oxygens. So you see that in the equation that's calculated the molar mass of that. And then barium nitrate, we need 1 barium, 2 nitrogens, and 6 oxygens to go through and calculate those. So I would expect that you know how to do the exact same thing. So pause the video, work through these molar masses, and we'll move on here in just a moment. All right, so same thing that we've done previously. Should be no issues here. We have 1 calcium and 2 bromines. So 1 calcium, 40.08. Again, that is based off of the information that is on the periodic table. We have 2 bromines, each at 79.90. We're going to multiply them and add them together. You might hear my neighbor mowing their lawn in the background because that's what they do. We end up with 199.88. And the unit we're going to start using for this is grams per mole. Sorry, mole. M-O-L. There you go. AlNO3, remember that's distributive property of math there. So we have 1 aluminum, 3 nitrogens, and 9 oxygens. So 1 aluminum at 26.98. 3 nitrogens at 14.01. And 9 oxygens at 16. And we just simply plug those into our calculator and solve. And we end up with 213.01 grams per mole. Okay. So again, just straightforward there. We've done this before. We'll continue to do this again moving forward. So whether it be in science or just in day-to-day life, we typically measure things in one of two ways. We measure things either in mass by weighing it in grams or pounds, whatever, or by the amount of something, and chemistry is no exception. So let's go back to let's go and think about oranges as an example. We measure them either by the pound or we measure by how many oranges we get in a bag. So I know when I go to Kroger, I buy apples, not by the pound, but I buy them by the bag. And so I buy them based off of the amount or how many oranges there are. And chemical reactions, interestingly enough, occur between number of atoms, not masses. So what's more important for us to know is not necessarily the masses of the materials we're combining together, albeit it's an important thing, but rather we need to understand how the atoms interact with one another and how many atoms of each we have, because that helps us understand how much product we end up getting. Atoms are small, and a large number of atoms are present in a relatively small sample, so we need a number that is relatively large in order to take into account the number of atoms that are present in an amount of something. And you can think of a mole as like a counting number. A mole is a number that we use in chemistry. A mole is like a dozen of something, right? Regardless of what you have, a dozen of something is always 12, or a ream of paper. A ream of paper is always 500 pieces of paper. A chemist's counting number is the mole, which is equal to 6.02 times 10 to the 23rd atoms or molecules, and that is equivalent to a mole of something. This is a big number due to the fact that atoms and molecules are very, very small. They're very tiny. And so it makes it very difficult to deal with large quantities of materials because the number of atoms is relatively large. This number in and of itself is known as Avogadro's number. And because this is the number of atoms or molecules per mole, we can use this as a conversion factor between atoms, molecules, and moles. So we're going to use this as a conversion factor to be able to convert between different amounts of a substance. So the first thing it asks us here says to determine the number of atoms in 0.250 moles of sulfur. So we're going back to our dimensional analysis that we've learned previously, but we're just going to be utilizing different ways to convert between two things. And I'll tell you right now, there's only two ways we're going to do this. We're going to go either between grams and moles, or we're going to go between moles and atoms, or the combination of the two. So the amount of stuff you have to memorize and know how to do with dimensional analysis with this part is pretty straightforward. There's only really a couple of conversions you're going to end up having to do here, but the rules are exactly the same as what we've done previously. The first step is always to identify the given and identify the unknown. The given is moles and the unknown is atoms. So we're going to set this up just like what we've done previously. Start with your given, and then whatever unit is on top of the previous step ends up going on the bottom of the subsequent step. We then utilize the fact that we know that there are 6.02 times 10 to the 23rd atoms of sulfur in an individual mole and set up our equation just like this. Moles of sulfur will cancel, leaving us atoms of sulfur behind, and whatever we go through and punch into our calculator, we just need to keep in mind that we round that to 3 significant figures. Again, make sure that you understand and know how to work exponents in your calculator. If you need help with that, check my previous video over measurements to be able to help you and help guide you with that. All right, so I've got 2 practice problems here that we're going to go through here in just a moment. Take a moment yourself, work through them, and we'll be back in a moment. All right, so we're going to start this out the exact same way we've done all of our previous dimensional analysis problems. Identify what is given and what is unknown. We start with 1.7 moles of calcium, and we want to determine the number of atoms from that. So start with what's given, 1.7 moles of calcium. Whatever unit is on top of the first step has to go on the bottom of the next step. And just to give you a little hint with all of this, your mole number here, at least for this class, now again, other classes are going to differ, but for this class, our mole number is always 1. So it makes this a whole lot easier to go through and figure out. We can use Avogadro's number to go between moles and atoms, so 6.02 times 10 to the 23rd. I need a little more room to work with this than some of the other numbers that we've dealt with. But again, the idea is still the same. The mole numbers will cancel, and what we're left with is atoms. Just make sure that you include your exponent when you go through and write out your answer. So what I get a lot of people that will tell me when they go through and do this, they'll end up with a 1.0 when they round to correct significant figures. But you need to look at your calculator. You've got an exponent that's there. And then don't forget your chemical formula as well. So again, pretty straightforward here. Determine the number of moles found in 3.42 times 10 to the 22nd molecules of CaCl2. So again, we start from the beginning. It's the exact same style of problem. The only difference is we're starting with a different material than what we did previously. Molecules on the bottom. Again, we use Avogadro's number. Our mole number is 1. Now, I want you to be very aware that when you write these types of answers, you notice that you have an exponent on top of the first step and an exponent on the bottom of the previous step. You should not have an exponent that is massive here. You shouldn't end up with anything that's times 10 to the 45th, 46th, etc. What that means is that if you did that and you got that exponent, you probably typed it into your calculator incorrectly. So be very careful. Make sure you round to the appropriate number of significant figures. And there you go. So again, it's just a practice in math, but that is a very important conversion factor that we can use. And notice we can go between atoms and moles, molecules and moles. The atom number, the molecule number is always Avogadro's number. The mole number is always 1. So it makes it pretty easy to know where to put which individual part, which makes this a little bit easier than some of the stuff that we've gone through and done previously. So we've already gone through and talked a little bit about formula mass and the calculation of the mass of a mole of something. I told you I wanted you to start using grams per mole as the unit for when we do stuff off of the periodic table. I've used the term molar mass already. I'll just reiterate. It's the mass in grams of a substance that is equal to 1 mole and the formula mass. So each of the elements on the periodic table, the decimalized number there is how many grams there are in 1 mole of something. Notice that as we increase on the periodic table, the numbers for molar mass get larger, and that's due to the fact that each individual atom is getting bigger. Remember, 1 mole of something is the same number of atoms. It's like the difference in weight between a dozen chicken eggs and a dozen ostrich eggs. You may still have a dozen of each of them, but the ostrich eggs are going to have more mass because each individual ostrich egg is bigger than that of the chicken egg. And it's the same thing here. A mole of iron atoms is 55.85 grams, while a mole of phosphorus atoms is 30.97. Well, that's because each individual iron atom weighs more than that of phosphorus. Once again, we can utilize this as a conversion factor, this gram to mole thing, as a way to convert between two different substances, just like what we've done previously. So given the moles of the substance, we can use a conversion factor involving molar mass to go to grams of a substance. Remember the numbers on the previous slide are how many grams there are in 1 mole, just like what we discussed previously. The 1 always goes with the moles when we do these types of conversions. So let's continue our work with an example here. It says, how many grams are there in 0.45 moles of NaNO3? Well, again, just like what we do with any type of dimensional analysis problem, you identify the unknown, or in the given, and our given here is 0.45 moles of NaNO3, and our unknown is grams of NaNO3. So we do our dimensional analysis. Before then, though, we need the molar mass. We know we're going to be converting between grams and moles, so I need that number off of the periodic table. Molar mass of sodium is 22.99, molar mass of nitrogen is 14.01, and then 3 times 16 for your oxygens is 85 grams per mole. And now we set up our dimensional analysis just like what we've done previously. Start with the information in the problem, which is 0.45 moles of NaNO3. 1 mole goes on the bottom of the next step, and I can convert directly between moles and grams. And I make sure that I round to the appropriate number of significant figures. It should be 0.45 moles, not 45. But you get the idea here. So it's the same process. We're just going between grams and moles. So I know it's difficult to keep in mind all of these different types of conversions, but I think the big thing to remember is that the mole number is always 1. You follow the steps like what we do with always with dimensional analysis. Whatever unit's on top of the first step goes on the bottom of the next step, and that really helps guide you as you move through this. Now, the big thing here is that you have to be flexible when using these conversions. Know what you can and cannot convert between. If we want to go between moles and grams, we're going to utilize the molar mass. If we're going between atoms and molecules to moles, we use Avogadro's number. There may be more than one step that's involved, depending upon where we're starting and where we're trying to go. So it's very important to read the question carefully, know what you can and cannot do. You cannot convert directly between grams and atoms of something. That is a no-go. You have to go through moles first. There is no direct conversion between atoms and grams. Look on the right-hand side here. I created this. Yes, if you Google this, mine will be like the first or second that pops up. You can quote me on that. This is the mole wheel. The mole wheel is designed to help you understand what you can and cannot convert between. So the biggest thing here with the mole wheel is identify where you're starting and where you're going. So let's say I want to go between moles and grams. Well, notice that there's an arrow between moles and grams that says molar mass, so I'm going to use the molar mass that's found on the periodic table. If I want to go between moles and atoms, molecules, or particles, I'm going to utilize Avogadro's number. But notice that if I'm going between atoms, molecules, and particles, and I want to go to grams, I cannot do it directly. I have to go to moles first in order to do that, because you don't want to cut the mole in half because the mole's going to have a really bad time. So that being said, you need to understand where we start and where we go. Now, you're not going to be given this on an exam, but this is a really nice tool to utilize in order to figure out where you're starting and where you're going. So I want us to calculate the mass of the following 9.96 times 10 to the 26th atoms of tellurium. All right, I'm going to do that here with you in just a moment. If you want, you can try it on your own. I'll tell you to go ahead and pause here if you wish, but I'm going to go through this with you here in just a minute. All right, so just like what we've done previously, identify what is given here. 9.96 times 10 to the 26th atoms of tellurium, and our unknown is mass. Remember, mass is grams. Start off with what's given. So 9.96 0.96 times 10 to the 26th atom. Whatever unit is on top of the first step has to go on the bottom of the next step. Now, using your mole wheel, remember we're trying to get to grams. The only thing I can convert with atoms is moles. I cannot go directly between atoms and grams. We use Avogadro's number here. Now we're not done, right? At the top of the step here, it says moles. We need to get grams. So we go another step. Now I can go between moles and grams. I just need to know the molar mass of tellurium. 127.60. Luckily I have a giant periodic table that's next to me. I mean, like, massive in my house. Just tells you what kind of nerd I am. Okay? Again, when you do the math with this, take it one step at a time. You should not end up with any funky, massively large exponent with this. Okay? Make sure you round to 3 sig figs. So we're going to take 9.96 times 10 to the 26th. We're going to divide 6.02 times 10 to the 23rd. And multiply by 127.60. So we end up here is a large number, but not a ridiculously large number. So 211,000 grams of tellurium. So a lot of tellurium, but that's also a lot of atoms of tellurium, all right? So again, one step at a time. Read the question carefully. Know where you're starting, know where you're going. Make sure you can plug these into your calculator correctly. Let's do 2 more here. It says determine the number of moles in 45 grams of acetic acid. We want moles, we're given grams. So start off again with what's given. In order to do this, we need the molar mass here. So to get the molar mass of acetic acid, we're going to take 4 times 1.01 plus 2 times 12.01 plus 32, or 2 times 16. So 60.06 is our molar mass. All right, and then we just do our math here. So 45 divided by 60.06, round to 3 sig figs. So 0.750 moles of acetic acid. The last question here says determine the number of molecules in the same sample. So we can start with moles if we want to because it is the same mole number from previous equation, but I want us to get into the habit of making sure we know where we start and where we're going from when we do these longer style problems. So I'm going to start with 45.0 grams of acetic acid again. I can only go from grams to moles, right? Cannot go directly between grams and molecules. So again, we're utilizing the molar mass we just calculated. And because we're going between grams and molecules, I need to make one more step and use Avogadro's number. Units cancel. We're just left with atoms. And again, go through and calculate. So 45 divided by 60.06, and we're going to multiply that by 6.02 times 10 to the 23rd. Round to 3 sig figs, we end up with 4.51 times 10 to the 23rd. Always write your chemical as well. All right. So I know that that's a lot to deal with and a lot to practice with, but it really is the culmination of all of the different things that we've been looking at really over the past couple of units. We're just kind of combining them into a chemistry form. So really make sure that you practice with those chemical equations. Make sure you practice with predicting products, balancing equations, those types of things. Also make sure that you practice with some of these conversion factors as well. Know where to start, know where to go. Make sure you look at that mole wheel as you work through and practice. That's the best thing I can tell you to do is just practice, practice, practice with this and you'll be great. We've got 3 more units left. We've got a solutions unit coming up. We have one over equilibrium and kinetics, that is the speed of a chemical reaction. And then lastly, we'll finish up with over acids and bases and maybe some gases if we have a little bit of time. But again, appreciate your time. Thank you so much for watching this. If you found this really helpful, really useful, leave a like, subscribe if you're interested in more chemistry content, and we will see you very soon for the next video. Bye, everybody. Have a great day, and happy chemistry-ing.